Welcome, everybody, to World Space Week. You may not have realized it was World Space Week, but it is. And SANSA has been celebrating by hosting learners every day. The UK Space School, what are they called? Yeah, the Space Academy, right. They're here. They gave a talk this afternoon. They'll teach some workshop on Friday, and tomorrow we'll have a teacher workshop, or is that on Friday also? Okay, more learners tomorrow. All right, so, and then we also have a public lecture, which is here live in Hermanus and also live everywhere on YouTube. And the title of my talk is Storms from the Sun, Protecting Tomorrow's Technology. And we'll hopefully explain what that all means. So I'm Marty Snow here at SANSA and also at the University of the Western Cape. And there's my email address. There we go. So here's the plans for what I'll talk about. I'll talk a little bit about what SANSA is and the Fast for Future project. Then I'll talk about the sun and space weather, what causes it, what its effects are, and then a little summary. So first, the South African National Space Agency, SANSA. We have three main campuses, Hermanus and Pretoria, and the one that I have difficulty saying, Hartbeespoort. Close enough, HBK. So at HBK, we do the satellite operations. So here's the picture of the dish. So command and control of satellites from space agencies around the world. And it has been operating for a long time, since the 1960s. I believe that it supported the Apollo launches and lunar missions. In Pretoria is where we have a group that does Earth observations, so satellite imagery of the ground to monitor land use, urbanization, agricultural use, and so on. And then, of course, we have the Hermanus branch right here. This is where we do space science. So we make geomagnetic measurements, do research in space science, space weather monitoring and forecasting, postgraduate mentorship. I say all these things because there's a forecaster and a student and so on in the audience. And we also have a ground-based instrumentation network all across Africa. So we do a lot of things here. The other project I wanted to talk about is this Focus on African Space Science and Technology for Future Development. It's a grant from the European Union. It's a 3-year project that has partners in several African countries and also a few in Europe. The map shows where the African partners are. And the goals are to strengthen science, technology, engineering, and mathematics, also known as STEM, in African higher education, and to promote the study of planetary and space science. Yeah, the sun also counts in there. And, of course, to promote international partnerships in science. So that's why you'll see all these logos on every slide. All right, so to talk about the sun, we realize that it's a star. And so you can compare it to other stars. So this plot is called the Hertzsprung-Russell diagram. It's a very common one used by astronomers. And I think I have a laser pointer here. There we go. And so on the bottom here is temperature, so how hot the star is. And then on the y-axis, the vertical axis, is how bright stars are. And as you can see, that they're not just scattered all over this diagram, that most of the stars fall in this band, and we call that the main sequence. And there's the sun. So it's kind of a yellow type middle temperature star, and this brightness is sort of relative to how bright the sun is, so that's why it's in the middle there. But there are stars that are hotter, there are stars that are bigger and cooler, there are stars that are hotter and bigger, and then there's these little tiny ones over here. So what does this tell us about the sun's characters itself? Here's a little picture of some scale models. So these are all scaled correctly in size obviously not in distance. And so compared to the sun, this little dot here is the size of the Earth. So the sun is 100 times wider than the Earth. So you can fit 100 suns across there, 100 Earths. So that's the big cat on the block. And then all the little planets are the little kitties. Even little Pluto there. All right, so inside the sun, there are three main regions. There is the core, which is where all of the nuclear fusion happens that produces the energy that makes the sun shine. So the gravity pulls the material close together. The atoms are close enough together to actually fuse, and hydrogen bonds together and creates helium atoms, and they also create all of the other elements. Then the energy works its way out through the radiative zone. This is where the particles of light kind of bounce from atom to atom, and it actually takes thousands of years for that to happen. It's a long way. Finally, it gets out to the outer layer where energy is now transported by convection. So the parcels of plasma move up to release their energy. Sort of like when you're heating up a pan of water. At first, the water just sits there and starts warming up, but eventually parcels of water move up to the top of the pot to release their energy, and that's what it looks like when it's boiling. I assume everyone has boiled water. And then, of course, the photons can escape out of the top. What's also important is this motion of these charged particles produces a magnetic field. And the magnetic field then makes the outer layers have variations. And I'll talk about the timescales that happens. Here is a picture of the sun. Okay, there it's back. It's alive. So this is a close-up of the surface of the sun in visible light from the DKIST telescope. I don't know why it stopped. There it goes. So you can see that there are these convection cells. The hot plasma comes up through the middle and then flows back down at the edges here. And for scale, this is the size of South Africa. If you look on the web, they will almost always compare these things to Texas. And I figured out that South Africa is twice as big as Texas. All right, so it takes thousands of years to get up to the convection zone, and then percolates up to the surface, and doesn't just come out as a blank sun. There are actually features on the sun. So this is over several days as the sun is rotating. So the sun takes about 27 days to rotate, and you can see that these dark spots appear seemingly out of nowhere. They're really coming up from below. And here's kind of our picture of what that looks like. So this little animation here zooms in under the surface of the sun. The magnetic field structures kind of can burst through the surface, and then now we're looking at it from above. You see these dark spots. So those are the sunspots. The magnetic field is very strong, and it prevents that convection from bringing energy up from below. So that part of the sun is cooler than the other parts. So that's why it looks dark. So just in diagrams, right, you have this, what we call a flux tube. So the magnetic field organizes itself in these structures, and it's kind of like having a magnet. And this is an image of the sun, and so the hot plasma can flow along the magnetic field lines, and so it highlights that arch. I think that's all we need to say there. Oh, no cat on that one. Okay, so the sun isn't always just very calm. Sometimes there are storms, and if this cat was good, he would be synchronized with the flare. So you can get eruptions on the sun that are caused by the magnetic field getting twisted up and relaxing to a lower energy state. It's kind of like when you're pulling apart a spring. If the spring breaks, suddenly it snaps and hits your fingers. So the same sort of thing can happen on the sun, but it releases X-rays and charged particles and possibly blobs of magnetized plasma. Here's what such a thing looks like in ultraviolet light. So this is a very short wavelength, so we need to observe this from space because all these wavelengths are absorbed by the Earth's atmosphere. There's the Earth to scale. So you can see these things are big. Let's try and run that one again. You can see there's lots of little sparks in here. That's the magnetic field reconnecting. And it releases a lot of energy. Sometimes these eruptions can produce not just light, but they also can spew material out into space. So the outer layers of the sun are called the corona, and mass being ejected from the corona is called a coronal mass ejection, because astronomers are really clever, right? So, or we call it a CME sometimes. So material coming out. Sorry for the poor taste. You can watch these eruptions spew out from the sun with an instrument that we call a coronagraph. So what it is it's a wide field camera, and we block out the light coming from the sun. That's what this occulting disk does. This white circle is the size of the sun. And so you can see the material out here in scattered light from the rest of the solar disk. So you'll see blobs pop out, big clouds and so on. One of the jobs of the space weather forecasters is to look at this seemingly 2D image and figure out, well, is this thing coming off to the side, coming sort of towards us, or just going off that way? So they have to measure its position. Probably they use computers to help, right? So figuring out where those things are going is important, because that magnetic field and hot plasma, if it hits the Earth, it can interact with the Earth's magnetic field, and we'll get to some of the effects of that shortly. All right, so the sun isn't just constantly bursting off. Sorry about the static. With these storms, there are kind of seasons on the sun. Sometimes it's more active than others. And if we look at a time series, so down here, this is time along the x-axis, so this is 1880 to 2020. All right. Thank you. Oh, I guess it's just got more squelch. Tapping works. All right, so for a moment I'll try and just speak loudly. So this is, more than 100 years worth of data, and this is the amount of the sun's surface that is covered by sunspots. So you can see there's kind of a pattern where it goes up and then comes back down. This period is about 11 years, and you can also look at where the sunspots are occurring. So at the beginning of a solar cycle, spots occur at fairly high latitude. If you can do the arc sine of 0.5 in your head, you'll know that that's about 30 degrees latitude, north or south. And then as the cycle progresses, spots start occurring closer to the equator. I guess I just have to hold the microphone much closer to my face. Okay. So a spot will last for a couple of months at most, and then new spots occur, and they start occurring closer and closer to the equator. So we, for some reason, refer to this as the butterfly diagram. Hey, move away, cat. So as you can see, it kind of looks like a butterfly. This pattern was recognized in sort of the 1940s. There was an astronomer who took credit for it but it turns out his wife is the one who actually figured this out. So that's a common thing, right? All right, so we can also have changes in the sun's output on short time scales, and this is what we call space weather. The sun has kind of a steady wind, but there's also these coronal mass ejections and particles and so on. And so here is one of our professionally made movies.
The advancement of space-based technology has brought about many benefits to our society. It helps us to communicate, to find our way, and to predict adverse weather conditions. It even helps us to plan our cities and towns. So what would happen if all our satellites stop working? It's unlikely that all our space-based technology will go out all at once. But a big space weather event could damage our satellites and ground infrastructure and cause issues with daily tasks. We rely on satellites for air traffic communications and weather prediction. We rely on satellites for navigation. Power grids are vulnerable to the onslaught of continuous space weather events. Modern farming methods are increasingly reliant on space-based technology for sowing, crop care, and harvesting support. We rely on satellites to provide time synchronization that allow for international money transfers and ATM banking. Space-based technologies are a catalyst for development, innovation, and creating a better life for all on this Earth. It is thus important to protect these technologies against threats such as space weather, which can harm technology and impact our daily lives. At the South African National Space Agency, we work around the clock to create products and services that will help mitigate the effects of space weather to our technologies to secure a better future for South Africans and the continent.
Scary space weather, right? Here's a diagram that shows many of the possible effects of space weather. So, of course, the sun up here is to blame for everything. We have spacecraft and astronauts and so on in outer space that could be affected by charged particles or X-rays and so on. Then we have a layer of the Earth's atmosphere where the high-energy photons, the ultraviolet light, has ripped some of the electrons off the molecules, making them ionized. And this ionosphere, right, it's a sphere of ions, is important because it will reflect radio waves. So those of us old enough to have listened to AM radio in our cars know that when you drive under a bridge, suddenly you have no radio. Similarly, if you want to try and communicate with an aircraft or something else over the horizon, you need to bounce the signal off the ionosphere. Well, when the sun erupts in X-rays, it changes the ionization of that ionosphere, and now you can no longer communicate with the airplane at the same frequency, or you need to change the volume or something. So that's one of the important customers for space weather, is talking to airplanes. Another thing, like you saw in the video, right? He was trying to navigate with the GPS, and during these solar storms, it can introduce errors in the GPS signal, or it can cause dropouts. And get to my favorite part of this diagram is, right, this little thing saying navigational errors, implying that the train is navigating rather than just driving on its tracks. But there are times when vehicles do actually need to know where they are. So this probably is uncommon in South Africa, but in many of the rest of the world, much of the rest of the world, there are times when a vehicle might be close to an edge and there is no visibility because it's in the middle of a blizzard or something like that. Then they're really relying on the position from the GPS satellites. So there he is. So speaking of satellites, this is an illustration of satellites in orbit around the Earth. So we have this distant ring of satellites at geostationary orbit. So they take 24 hours to orbit the Earth, which means that they go at the same rate that the Earth rotates. So they appear to stay in the same spot in the sky, right? That's why your DSTV dish doesn't need to try and track a satellite. It just points at one spot in the sky, and that's where the satellite always is. As you get closer in, you can see that there are a hive of angry bees, also known as the low Earth orbit satellites. So those take about an hour and a half to orbit the Earth, so you can put science instruments on those or communications and so on. There are many, many tasks for it, but the point is there are a lot of satellites. Our joke is that the primary constituent of the thermosphere is aluminum from all these satellites. So, Elon Musk is in the news again today at the IAC conference. But a year ago, a little bit more than a year ago, there was an issue with a launch of some Starlink satellites. So Starlink is this network of satellites that are going to provide internet connectivity around the world. There are going to be thousands and thousands of these satellites, and they launch them, 50 at a time or so. And there was a time last February when they launched, I think, 47 satellites, and 40 of the 47 then crashed back into the atmosphere and burned. So that we figure these little modules are $250,000 or $500,000 each. The launch itself is another $30 million. So suddenly, there's a lot of money lost on these satellite failures. So, what happened? There was a geomagnetic storm. There was a geomagnetic storm right after they launched. So they went up to a low orbit to start with, and a storm from the sun increased the atmospheric density, and since they were only at 200 kilometers, a small change in percentage meant that there was suddenly a lot more drag on those satellites, and that's why they all crashed. So I guess I left out the next slide, which was the SANSA bulletin from the day before saying, careful, there's a G1 storm on the way. You might not want to launch your satellites today. We've heard that SpaceX now pays a little bit more attention to the space weather forecasts. So, I mentioned that the X-rays from the sun change the ionization of the atmosphere. Is this going? Yes, it just goes very slowly. So this is an animation of a model of the upper atmosphere, and this is the ionization of the atmosphere, and the colors say what radio frequencies are absorbed, and this is moving slowly across the map because the Earth is rotating. So it's essentially the point above the Earth where the sun is, the subsolar point, and it moves around. So during an outburst, you start to absorb very, very high frequencies. So you would need to switch to a lower frequency. And those of you who are electrical engineers know something about information content as a function of frequency. I don't know that. I can just say the words. All right. So how do we figure out where these blobs are going? Well, we use sophisticated computer models. And this one shows the sun at the center, and this is where the Earth is. So there are these sort of underlying streams of particles. This is a plot of density, and this one shows velocity. And so you can see that right now the Earth is in a little bit of a higher density region. So that's this elevated part. The vertical line shows the time of the model result. And as we get farther along here, see it's doing like one slide per hour, one frame per hour. So you got to be patient, right? You got to let the storm occur. The velocity is starting to go up from this big band here, and eventually, can I zoom up a little bit? Ooh, yeah, I can. All right. You can see that there's a blob coming off the sun, and you say, oh, is that going to hit us? Is that going to hit us? And you call the space weather forecasters and you say, Ketekile, are we safe? And she says, yeah, you'll be fine. So figuring out exactly where this enhancement is going. Is it going to hit the Earth? Is it going to miss the Earth? Is what the forecasters do. So here's a picture of the Earth and its accompanying magnetic field. So there's a constant solar wind that kind of deforms it so it's not symmetric. But the solar wind coming this way is usually deflected by the magnetosphere. If there's a blob of magnetic field that hits it, if it's pointed the wrong way, then the two magnetic fields will interact and there will be reconnection. And then all these particles in the solar wind can sneak into the atmosphere. In the normal case, the magnetic field is parallel in the magnetosphere and the solar wind, and the blobs of magnetized plasma just sort of sneak on by. I have a movie here. So there's the Earth, and you can hopefully see all the little charged particles zooming by, and this is a simulation of what that big blob of ionized plasma might look like. So you can see there's the Earth, and the magnetic field of the Earth is protecting us. All those particles are being pushed to the side. Yay, magnetic field. Some of the field lines kind of point out towards the interplanetary space and not just parallel to it. Particles often can sneak in there, and they hit the Earth in the north and south, and they produce the aurora. So that's high energy particles hitting the atmosphere, exciting the atoms, which then radiate different colors. So that's the story for the Earth. What about other planets, right? So here they are in order and kind of relative size. The distances are not the same. But there's these little rocky planets, and then there's the big gas giants. So they also typically have magnetic fields and magnetospheres. And here is a diagram showing the size of the sun. So you can see that Jupiter's magnetic field is enormous, right? It's much bigger than the sun. And Saturn's magnetosphere is probably about the same size as the sun. As I mentioned, particles can sneak through the magnetosphere on Earth and produce the aurora in the north and south. And that also happens on other planets. So this is an image of the aurora on Jupiter that was captured by the Hubble Space Telescope. So you can see the exciting particles are tracing out where those particles hit. So you get the big kitty and the little kitty. So what about other planets? They don't all have strong magnetic fields. And the big example is Mars. So Mars it's a little bit farther from the sun, so you might think it's a little cooler, but it's not that much farther, and it's a lot colder. What has happened to Mars? This is one of the big reasons that we send all these probes to Mars, is to figure out, why is Mars the way it is? Well, it turns out that Mars does not have a global magnetic field. Right? It's got some local surface magnetic fields, but it doesn't have a big protective shield the way the Earth does. So in this picture, the Earth's magnetic field is deflecting all the solar wind particles. Well, all those solar wind particles can hit the surface of Mars. And over the last few billion years, they have stripped away almost all of the atmosphere from Mars. So that's why Mars has such a tenuous atmosphere now. And that means that it radiates all of its solar energy back out to space, and that's why it's so cold. So, yay, magnetic field. Right? So on Earth, it's warm enough to have liquid water on the surface. If there's bits of water on Mars, they're usually in the shadowed regions and so on. So, the lack of the magnetic field is what has turned Mars into this wasteland, and luckily has not happened on the Earth. How about if you have no atmosphere at all? This is an image, I guess it's a drawing, of a satellite called OSIRIS-REx. So what its job is to fly out to an asteroid, and here's a bit of its camera watching its little arm extend out, and it grabbed a handful of rocks and dirt off this asteroid, put it in its little container, and then came back to Earth. And it landed about a week ago. So this module has the rock samples from the surface of an asteroid. So we can see what happens to bits of rock that have been out in the solar wind with no atmosphere or magnetic field protecting them. So we have a better idea of what the solar system started out as, right? This is pristine material that has never been processed by an atmosphere. So it just landed. It'll be a while before we have real results, but probably at the next conference anybody goes to, there'll be a lot of results. He's just digging. All right, so I have one more.
Why is it important? What is the threat? What is the impact on technology? How does it differ from terrestrial weather? What is space weather? The Earth, our home, orbits our life-giving star called the Sun. The Sun is not only extremely hot, with a surface temperature of about 6,000 degrees Celsius, but it also has certain activities happening on its surface, like solar flares, coronal mass ejections, storms, and heat, basically emitting millions of particles, radiation, and energy into space. This causes space weather. And even though the Sun is about 150 million kilometers away from Earth, our planet can still be affected by space weather. Just like Earth's weather has seasons, space weather has seasons too. The Sun has a cycle of about 11 years, known as solar minimum with low solar activity and solar maximum with high solar activity. But even during times of low solar activity, solar storms and solar flares may occur. Solar flares are giant explosions on the surface of the Sun that occur when twisted magnetic field lines suddenly snap and release massive amounts of electromagnetic energy. A solar flare takes about 8 minutes to reach Earth and travels at the speed of light. Charged particles from solar storms can reach the Earth in a mere 20 minutes, while coronal mass ejections, which is a large cloud of charged particles, will take 1 to 4 days to reach the Earth. When the magnetic field of a coronal mass ejection interacts with the Earth's magnetic field, it causes a temporary disturbance known as a geomagnetic storm. Space weather is constantly interacting with our Earth's magnetic field, but the impact of a space weather storm will not harm humans and other life forms on Earth, as we are protected by the Earth's magnetic field. The Earth is a giant magnet, and the field it generates acts like a shield against solar particles and radiation. However, our astronauts, the aviation sector, and satellites are at risk. If satellites are hit by space weather, radio communications, telecommunications, navigation and weather services may be affected, and many more electronics can suffer hardware errors and failures. This can disturb internet connectivity, have an effect on your cell phone, interrupt satellite TV, and even cause radio blackouts. In severe cases, the power grid may be damaged. Astronauts also have to be aware of space weather and should avoid spacewalks during space weather events in order to avoid the radiation from the Sun. Passengers and crew on long-haul flights can also be exposed to radiation during space weather events, which is why the International Civil Aviation Organization recommends that space weather information be included into flight plans. But the effects of space weather interacting with our magnetic field can also be spectacular. The magical lights in the sky called aurora are an effect of space weather storms such as solar wind, solar energetic particles, and coronal mass ejections. And while we enjoy the beautiful views from our balconies, looking up into the sky, we can remember that our magnetic field is working non-stop to keep our planet safe. Scientists from around the world are constantly monitoring the sun and our magnetic field to predict space weather and warn of their effects. The South African National Space Agency is expanding to do this on a 24/7 basis and offers several products and services to mitigate the effects that space weather may have.
See, we're the good ones. All right, hopefully everything in that little video was reviewed that I had mentioned earlier. And so that's all I wanted to cover, and I'll open it up for questions in case anybody has a burning question. So like if there was a flare happening, so those are not continual. I mean, the solar wind is kind of continuous at a certain level, and when there is a big disruption from a flare or something, those satellites can have upsets. The electronics can fail, so they may have to reboot the computer and so on. But depending on the way the data is stored, it's probably not lost forever, and you can maybe send it again an hour later. But that's a great question. Yeah, Bob? Yeah, they're right. So the space weather effects are, in the very high in the thermosphere down to the ionosphere, and the weather patterns and so on are from the ground up to maybe 100 kilometers into the stratosphere. So the one area where they might interact a little bit is that the ultraviolet light from the sun is what creates or destroys ozone, which allows more ultraviolet light to reach lower down. So the solar cycle, the 11-year period, does affect the amount of ozone we have. But in terms of like storms and global warming and climate change, space weather doesn't affect that. Right, that this is magnetic fields and charged particles instead of temperature distributions and pressure differences that produce winds and so on. So they are pretty distinct. But that's a great question. Yes? So every 11 years, the nation's scientists all get together to try and predict the severity of the next solar cycle. And so if we look back to the butterfly diagram, I guess I don't have a really good. So we do look at long-term patterns of, okay, well, there was a big cycle and then a small cycle and so on. Is that part of what's going on? And if you look at, so this is showing where the magnetic, or where the sunspots are, but you can make a similar diagram of just the strength of the magnetic field. And during the cycle, the sunspots start migrating towards the equator, but a lot of the magnetic field is carried up to the poles. And a way that we predict the next cycle, or a few cycles ahead, is the strength of the magnetic field at the poles of the sun. So part of the uncertainty is, all right, the magnetic field gets pulled up to the poles and sucked down into the convection zone somehow, and then how long does it take to move back down before it can come back to the surface? Is that one cycle? Does it take 2 cycles? Is it a conveyor belt that lasts 4 cycles? And so there are many different models that try and predict what's going to happen the next cycle. And, sometimes they're right, sometimes they're wrong. Almost everybody predicted that the current solar cycle was going to be small, like the one that just ended. Of course, I had one friend who said, no, if you look at this other data, it says this cycle is going to be at least as big as the one a few cycles ago. And sure enough, we're currently in the rising phase of cycle 25, and it is way above what, 100 out of the 101 models predicted. So my one friend back in Boulder, he's the one who was right. But it is an area of active research. You try and model exactly what's going on with all the magnetic field, as you can imagine. A three-dimensional, magnetohydrodynamics to figure out where the magnetic field is getting pushed and pulled to, and so on, is very complicated. And so there's a lot of approximations that need to be made, and some of them maybe aren't the right approximations. So it's an area of active research. Maybe you're thinking of doing a PhD? Yeah. No, it's a great question, and something that we really want to know, right? What's the sun going to be like tomorrow is one question, which Katakile answers every day. And then the next question is, what's the sun going to be like 5 years from now, right? Do I start planning a space mission that's going to launch 5 years from now, or should I wait so that it launches 10 years from now? Yes? So Mercury has basically no atmosphere, and I believe it also has no global magnetic field. I think the solar wind strikes the surface, and it sputters off lots of ions and elements. You can see what looks like a tail from Mercury, and it's like sodium ions and so on that have come up from the rocks on the surface. So I'm not, without an atmosphere, it's not going to change the temperature and so on, right? Mercury is mostly, for those of you who don't know, Mercury, the closest planet, also it rotates at the same rate as it goes around the sun. So the same face is always pointed towards the sun, kind of like the moon, right, is tidally locked to the Earth. So we always see the same side of it. Right? It rotates around the Earth at the same rate that it rotates on its axis. So, I think that's probably dominating any of the space weather effects on Mercury. But Mercury is another place of mystery that it wasn't until recently, 10 years or so ago, that we had satellites that routinely could exist around Mercury. Right? It's hot. Before you had to just kind of zoom by, right? But that's a good question. Yeah. Blue giants. So we do see cycles in magnetic activity in many stars, and some of them do produce flares and so on. And as we now know, there are planets around most stars, right? The number of exoplanets that have been discovered, jumps by an order of magnitude every year. And so there are space weather effects on those other planets. I think, in general, the cooler stars are the ones that have the right ratio of convection to ionization to produce the magnetic fields. That I think those blue supergiants have a lot less of a magnetic field. I could be wrong. I always study the cooler stars because they're cool, right? But that's a great question. And in fact, one of the very nearby stars, Proxima Centauri, was recently seen to have a big flare. And it has some planets, and it's thought that if there was a planet at the right spot, that flare was big enough to have potentially really damaged the atmosphere of that planet. And so, luckily, our sun has never done anything like that. We have had some pretty big flares. The most famous one is from 1859. Before we had a lot of technology, there was an enormous flare. It was one of the first flares that we sort of were looking at in the right way to see. And then a few days later, there was a big geomagnetic storm. At the time, the technology was telegraph wires stretched across big regions of the Earth. And there were reports of the telegraph station catching fire from an induced electric current, or they removed the batteries and they could still run the equipment. So if something like that happened today, it could cause long-term damage to like the power grid, right, which might take years to repair. Uh-oh, it's raining. And so yes, other stars can have big flares, but luckily our sun has not had such a big flare that it would damage us. Can you say that again, please? Oh, the gas giants. Okay. I thought you were talking about the first Hertzsprung-Russell diagram with the big blue giants in the corner there. Okay, sorry, I misunderstood that. Yeah. I thought you were asking about, right at the beginning, right? Didn't you have a question before we even started? So, right, the big gas giants. They also do suffer space weather effects. That image of Jupiter, right? So this is Jupiter's huge magnetosphere, and so it has the similar shape to the Earth in that it's a dipole with these little cusps and so on. So you can get charged particles that come in here. Jupiter also has many moons. And one of the moons, Io, has volcanoes on it, right? And so it is spewing ionized sulfur out into the region around here, and those ions are trapped in in Jupiter's magnetosphere, and you can actually. So this, I think this caption is not quite right, because I think this is actually the foot point of where the magnetic field from Io connects to the surface of Jupiter there. So I think these are the ion trails as that moon goes around. So I know the caption says it's the aurora, and I think some of it is, but I think this one is the foot point of that moon. So there definitely are space weather effects on the gas giants. Even though they're quite a bit farther away from the sun than the Earth, they still, are not so far away that they can escape the sun's magnetic field. Yes? So the other stars, so those couldn't hear, it's can you have a space weather event from a different star that affects us here on Earth? So space weather in terms of this kind of particles, probably not, because those other stars are so far away that by the time you disperse over the area of the sphere that's around that, when it's 4 light years away or 10 light years away and so on, there's hardly anything here. But there are very energetic events out in the universe, right? There are supernovae. Right? So a whole star explodes, and it produces a lot of energy. It also produces a lot of high-energy particles, which we call cosmic rays. So we are constantly being bombarded with cosmic rays, and luckily our sun's magnetic field deflects most of those, because they're little charged particles, and the Earth's magnetic field also deflects some of them. We can measure those from the ground because those cosmic rays hit the upper atmosphere, and they'll hit a molecule and knock neutrons out of the nucleus, and we can detect those neutrons. So in a building a few hundred meters away, we have a neutron monitor, and you can detect the number of neutrons as a function of time, and it is, of course, exactly opposite to the solar cycle. When the sun's magnetic field is small, more of those cosmic rays hit the Earth. When the sun is active and protects everything, there are fewer of those neutrons. So we do see the effect of supernova from around the galaxy and in other galaxies and so on. And there's a lot of those little particles. So back to your question of, well, how does it affect weather? And so there's a lot of work being done to understand the effect of those galactic cosmic rays on the upper atmosphere, because they're, the spallation and so on can actually seed cloud formation. So the cosmic rays can be correlated to cloud cover, which does have an effect on climate, at least regionally, if not globally. So I gave kind of a simple answer to your complicated question, and so I'm now making my answer a little more complicated since somebody brought in cosmic rays. So it is a very complicated system with many interconnected parts. So that's where events on other stars and other distant galaxies and so on do have an effect on us. Is anybody chiming in from online? No, they're all sleeping. They're all waiting for the link. That's okay. It'll be on YouTube for forever, or at least until the sun goes supernova. All right. Well, thanks everyone for coming, and hopefully it was enjoyable. And we'll continue with our Space Week events for the rest of the week here and throughout the world. All right. Thanks. Postpone.